this, scheduled prelims exactly at this time, so he couldn't make it, and that's why I'm giving the talk instead of him. And all right, so here's the overview. I will focus on the statistics part of this. I know that the title is like on the role of entanglement and statistics in learning, so this is going to be mostly about the statistics part, actually exclusively about the statistics part of that thing. And the main result here is actually a separation between learning from quantum examples and learning by estimation of observables, from basically expectation values. To be able to introduce it, I will review some basic statistical learning theory. Then I will talk about quantum statistical query learning, and then I'll give you a proof sketch and wrap up with a discussion. So let me give you a bit of a statistical learning theory refresher. So whenever you want to, statistical learning theory is a mathematical framework in which you can reason about learning problems. You can prove lower bounds, and also design algorithms. And to be able to do this, you need to define what a learning problem is, and in order to be able to do that, you have to use notions like instance space. So an instance space is a set over which you learn. You also have to define a notion of a concept. So a concept is going to be some subset of the instance space. And generally, learning problems are going to be characterized in terms of a concept class. So concept class is a set of concepts, that essentially define your problem. So to be more concrete, if you want to classify handwritten digits, your instance space may be, grayscale images of, handwritten digits. And a concept could be the set of all handwritten digits. 8. All right. And then the game you play here is that you have an oracle that takes a concept from the concept class, hides it from you, and it has a bigger button. And if you press the button, it will tell you some information about the concept. And the way it tells you the information may actually depend on the some unknown data distribution as well. So the data distribution is just a distribution over the instance space. And your goal as a learner is going to be to interact with the oracle and formulate a hypothesis H that approximates the hidden concept. And in order to be able to, reason about this mathematically, you still need to define a couple of things. So one of the first thing is what do the oracle queries, or the responses to the oracle queries actually reveal to you, and what counts as a good hypothesis. So let me start with the second thing. What hypothesis is good? Well, generally it's going to be the hypothesis that we generalize as well. What hypothesis generalizes well? Well, it's going to be the hypothesis that is as close as it can be to the target concept. So basically the probability that a randomly drawn sample from the target hidden distribution, that basically your hypothesis disagrees with the target concept on a random sample drawn from the target distribution, is the error that you're trying to minimize. Now, of course, as a learner, you will never have direct access to this because the data distribution is hidden from you, and so is the concept because you're trying to learn it. But, at least you can try to upper bound it by doing things like empirical risk minimization. And so what does it mean within this framework to learn a problem? Well, that's formulated in the notion of probable approximately correct learning. For any epsilon and delta between 0 and 1/2, for every C in your concept class, and you know what the concept class is here, and for any D, you aim to find a hypothesis H such that the probability of the average error being greater than epsilon is upper bounded by delta. And I'm sure that a lot of you know this definition very well. You will call a problem efficiently learnable if you need to make polynomially many queries in one over epsilon and one over delta. This is an information theoretic notion of learnability. And if you care about computational efficiency, you may also say that you impose that you need to be polynomial in N if your instance space is, the set of bit strings, and that's a technical. All right. So now that I told you what hypothesis counts as good, let's get to the oracles. So for essentially every oracle that I'll introduce here is going to define a learning model, right? And so the most basic oracle that people deal with, those defined by Valiant, is the random example oracle. You press a button and out comes a labeled example. Like you sample X from your data distribution and a label. And this is quite nice and straightforward. The learnability in this model is nicely characterized by a combinatorial parameter called the VC dimension, and this model is well understood, right? The next oracle that I'll need to introduce statistical queries is learning from random examples under noise. So it's the same as the above one, except that with some small probability, your labels get corrupted. So, like whatever was labeled as 0 may get labeled by 1, and vice versa. All right. So let me run through very briefly an example from Kirsis and Vazirani's book, which is the learning of conjunctions. Here the concept class is a set of conjunctions over at most n variables. And it goes over all literals. So every variable can appear, like negated or not negated. And unfortunately, it's almost illegible here. I'm really sorry about this, but this concept class is nicely, efficiently pack-learnable. And it's pack-learnable by the following algorithm. You start with a hypothesis that contains all the possible literals that you can have. So that the hypothesis has to 3n literals. And if you see a positively labeled sample, that basically means that like it's an assignment of your Boolean variables that evaluates to true in the target concept, you will just delete all the literals that are inconsistent with what you see in the sample, right? And this way you can very quickly get to the target concept. Like Converge is really nice. With every positive sample, you will delete a lot of literals, and everything is nice. The reason why I talk about this, though, is that if you try to use the same algorithm, that goes literally like positive sample by positive sample and deletes those literals with noise, then a single sample that was labeled as negative and flipped to positive is going to destroy your algorithm completely, right? So what can you do about it? Well, you can collect samples, and if you see some sample that says, hey, look, this literal is inconsistent with what I'm seeing, you will not delete the literal from your hypothesis that you're trying to formulate, but you will just reduce your belief that the literal belongs to, like your target hypothesis that you want to formulate. And at the end of the algorithm, you just threshold and keep everything that is above threshold. And this way, you actually make the algorithm robust to the label noise. So in other words, you are taking statistics over the samples that you're taking. And at the end of the algorithm, you evaluate the statistics and you use that to formulate the hypothesis. And this way, you basically go from an algorithm that's really fragile to the label noise to something that is robust to the label noise, just by averaging and collecting statistics, right? And this strategy works so often that Kieran's actually used this to define another oracle called the statistical query learning oracle. And that oracle, is quite interesting because it takes an input. That input is some Boolean predicate, that actually you takes as the input, the labeled sample. And the oracle, has a bigger button. You feed it the Boolean predicate. You press the button, and it gives you an approximation to the probability that a given that your predicate evaluates to true on a given labeled sample. If you are drawing, samples from the hidden data distribution, okay, and you get that quantity only up to tau approximation. So tau is some parameter. If you want to have an efficient statistical query learner, every chi that you're feeding in has to be evaluatable in polynomial time in 1/n. Tau inverse has to be bounded by polynomial. And then, of course, you have to satisfy the pack guarantees in order for things to be learnable. There is a combinatorial parameter that characterizes learnability in this model called the statistical dimension, and I will talk about it a bit more in a couple of slides. All right, so the next question you may ask, well, if that strategy worked for learning conjunctions, does it work for any problem? You know, like, can I literally just like take statistics and make every problem that was learnable in noisy pack? And the answer is no. And the concept class that splits these two learning models is the class of parities. You know, as defined above. To give you some intuition as to why is it so, you know, when you're learning from random examples, you collect enough samples to build a linear system out of which you get, you know, like the target parity, you know, by matrix inversion or like by Gaussian elimination. And it turns out that this is extremely difficult to do with SQ. And in SQ, on the other hand, you can show that no matter what query you make to the oracle, the response to the query will not reveal enough information about the hidden concept. And the way you can show this is that you can bound the variance over uniformly random concept, you know, the variance actually of the response of the oracle, you know. Okay. So this is the situation. You know, like the red circle is the set of you know, like all problems that are solvable with random examples. You know, the white circle are all the learning problems that are solvable with statistical queries, and it is separated by the concept class of parities. Right? All right. And since this is a quantum conference, I have to start talking about quantum learning models as well. So we have two. Actually, the top model was defined in a paper by Choate and Jackson, but I have two references here. You know, like one to paper by Savardi and Gortler, the other one to paper by Srinivasan and DeWolf. You know, that made some important contributions to this. This is called the quantum example oracle. You press a button and out comes a coherent encoding the distribution and the labeled samples. Right? Okay, well, you know, like you may wonder how it compares to the random example oracle, and if you do wonder about it, then please read one of those papers. But you can actually, similarly to what happened with the random example oracle on the classical side, you can actually formulate a quantum statistical query learning oracle similarly by, you know, instead of feeding in like Boolean functions, you can now start feeding in observables. So these are positive semi-definite matrices on your input. They are, you know, bounded in the operator norm, and the oracle has a bigger button. If you press the button, it gives you an approximation to the expectation value of your observable evaluated over some, you know, over the, you know, like hidden concept. I mean, like here, actually, rho is this state here, just as, you know, like a density matrix. But you can see that this model is quite easy to extend to concept classes over quantum states, which we also do. Okay, so this way you can see this model as learning from expectation values. And you know, that also motivates it because you can say that because we have error mitigation, you know, and other techniques like this, it might be more experimentally accessible, right? In principle. Also notice that it doesn't have any quantum memory. Like all these observables, all these expectation values run over a single copy of the target state. So this is quite important. Actually, you know, like shameless plug, Alex will be talking about this. You know, Alex Nieder will be given a poster presentation about the generalization of this model where you have multiple copies. So, you know, like if you're interested in this, go and talk to him. The key question to ask now is that, as you've seen, the random examples and the statistical queries are separated by the concept class of parities, learning parities. Does this separate quantum, you know, examples and quantum statistical queries as well? And the answer is no. There is actually a simple algorithm that you can use to learn parities in QSQ. It comes with a caveat now that we are no longer in distribution independent setting. We are fixing the distribution, the data distribution of the oracle hides to uniform. But under that caveat, like, yes, that is an algorithm. And so if you fix the distribution to uniform, you know, like, and you know that you know, like, parities don't separate the two learning classes, you may wonder what the problem actually separates them. This is the question that we addressed in our work and also managed to answer. All right, so separating quantum, you know, random examples or quantum examples and QSQ. So here we took, I mean, there is a beautiful line of work on the classical side about proving lower bounds on statistical query complexity by Feldman. And it, you know, like, basically the last paper on this is this one, the general characterization of the statistical query complexity. And in those papers, like, he's deriving combinatorial parameters that can be used to lower bound the statistical query complexity. And so basically here, you know, like, you may wonder how much of this goes through quantumly. And, you know, if you can use these techniques to actually, like, find the task that separates the two learning models that I introduced on the previous slide. And, you know, like, by and large, the idea here, you know, it's a recurring theme in learning theory, but, like, we are still aiming to show that, like, no single query that you're going to make to these oracles is going to be able to differentiate large fractions of the concepts that the oracle has. So, and the way we do this is that we follow the template that Feldman laid out. You know, so he starts by looking at something called many versus one decision tasks in, you know, statistical queries. In our case, it's quantum formulation of that. So in quantum statistical query learning, the many versus one decision task is a task where I give you a state row that comes either from some set S or some reference state sigma. And your goal is to use queries to qstat tau oracle to figure out whether I give you sigma or the set S. The number of queries this is going to take you is called QQC S of sigma in our paper, at least, and it's parameterized by tau. Right. And what is quite nice is that you can reduce the learning with quantum statistical queries to many versus one decision tasks. Right. So you can see, you know, here, if I take the many versus one decision problem and I give you some promise on the distance of the reference state from the target set, you know, I can show that, you know, like, the quantum statistical query learning at with the average error epsilon, you know, and, like, the approximation level tau is lower bounded by QQC tau, you know, like -1. This is one query difference. Okay. And what remains is to define the combinatorial, like an analog of the combinatorial parameter that Feldman defines for statistical query learning, which is the quantum statistical dimension. And roughly, you should understand it as the smallest expected number of observables that can distinguish the concept class C from some reference state sigma in the many versus one decision task. Okay. Yes.
The reference state sigma.
Yes. Let's go to the next slide.
Okay.
And then we can talk about it a bit more. Yeah. Okay. So anyway, there's a lower bound, you know, like by the quantum statistical dimension, and it lower bounds the many versus one decision task. And so this is the template, you know, that I'm using here. You have the quantum statistical dimension. You know that there is a, you know, like through that there is a that, you know, this quantity lower bounds up to factors the many versus one decision, you know, complexity, and that lower bounds the complexity of quantum statistical query learning, which is the target quantity we want to lower bound. And so what remains is that you have to figure out how to lower bound the quantum statistical dimension. And the way we do this, is not dissimilar to what is happening in the proof, that parities are hard to learn with SQ. You, basically bounded the variance. You bound the variance of, sorry, you take a distribution, right? Like over your concepts, like here rho, it corresponds to the target concept. And you have to ensure that the average itself, you choose the distribution such that the average itself isn't in the concept class. Well, then you bound the variance over that, and there's a nice lower bound that follows. And the idea behind all of this is basically like no query that you are making to the quantum statistical oracle reveals again enough information about like a large fraction of concepts. This is the recurring theme here. And that was the same idea in the Kieran's proof, that showed that parities are not learnable by statistical queries, right? So this somewhat like touches on your question, right? Because this is how we build the reference state. The reference state here is the average. It's basically the weighted average over the concept. Right? But you can engineer it in all sorts of way, and it's very like problem specific. So.
Normally the way to get rid of that state and then have a quantity minimization.
Sure. Yeah. Yeah. I mean, we can talk about it later. Let's finish this. But okay. All right. So and then. This is how we separate, the quantum statistical query learning and, quantum examples. The separation goes through, by concept class of degree 2 Boolean functions that actually appeared in work of Srinivasan, Akopal, Bravi, Yoder, where they show that this concept class is actually learnable from quantum examples. And in this paper, we show that while it is learnable from quantum examples, it is not learnable by quantum statistical queries. And by that, we separate the two learning models. Okay, and that's the result. So we do have some additional results in the paper, which are applications of this machinery to other interesting problems. We have results on, say, hardness of testing purity with quantum statistical queries. We looked at the abelian heading subgroup problem. We do have some results on shadow tomography as well. We studied precision thresholds in QSQ, which are an interesting theme on the classical side as well, and so on. There was also like a small result, I mean. There was an open result from previous work, and the epsilon approximated, or like pushed epsilon further, which is that there is this notion of weak and strong error mitigation that was formulated in this paper by Ihoikwek and co-authors, and they were asking whether like the notion of weak error mitigation could also imply strong error mitigation, and they were able to refute it. In the case where effectively you were using quantum statistical queries with diagonal observables only, and so here we managed to complete the proof, and with arbitrary queries to the quantum statistical query oracle. So this is another application, and that's it. Thank you so much.
Thanks very much for the talk. We have time for 1 or 2 questions if anyone has questions. There's one question there.
Thanks for the talk, Wojta. So the upper bound that you cited for learning these quadratic function states comes from Bell sampling algorithms, right?
Yeah, if I remember
So
correctly, yes. I think Archipel is sitting right behind you. So if he nods, then the answer
okay,
is
if he
yes.
nods, then it's fine. So does that mean that if we look at 2-copy QSQs, which you said you're like explicitly excluding, but say we look at those,
Yes.
then presumably it should again be easy?
That's a good question. I don't know. I would expect it to be the case. Alex might know better.
You mean in stabilizer learning?
Yeah, but
Like for stabilizers, it's also hard from 2-copy QSQs.
Okay. That I didn't know. It seems surprising. Thanks. Oh yeah, please go to
Thursday, right?
go and see Alex's poster. He's gonna explain to you.
Any other questions? I have time for one more question. I have a very annoying question. Like,
Yeah, please.
I don't know if that makes sense, but how would you, because you consider entanglement, what if you allow like super quantum correlations? How did your results?
I don't think we studied this, but I mean the thing is that like the entanglement part, like I didn't really touch upon it, here. You know, like it only appeared like sort of on tangent. You know, I was talking about the fact that like there's like just one copy of the state, you know, and in this specific mode. But then we have another result in the paper that specifically touches on, you know, like the difference between like separable and entangled measurements and learning from quantum examples. So it's a slightly different result. Super quantum correlations, like I don't know, like we haven't studied this, and I don't even know like how would I, you know, like maybe formulate something like on statistical query learning, you know, like
I guess have to formulate on a black box perspective, right?
That's true. That is true. I would be curious, like how will the oracle, you know, look like?
It's a good question. Okay, last thing to speak again.
All right, thanks so much.
Come on in. Okay, I guess we can start. So for the second and final talk of this session, we welcome Xue, to talk about mean estimation. Please take it away. Okay.
Oh, okay. So very glad to participate our paper quantum non-identical mean estimation. I'm Xue Yecheng, and this is a joint work with my lab mate Wang Xinzhao, my advisor Li Hongyang, and my collaborates Zhang Chenyi from Stanford University and Hu Dachen Zhonghan from Peking University. So in this paper, we analyze a new setting of the quantum mean estimation problem. We focus on the non-identical quantum random variables. We systematically analyze this new setting about the upper bound, the lower bound. We define what is the non-identity of quantum random variables, and we will see how it makes the quantum mean estimation problem different. So let's just begin from the IID case. So assume that we are given n random samples. They are independent and identically distributed with a mean mu variance sigma square. And our task is to estimate mu to some additive error epsilon. So for this problem, for classical computers, the upper bound and the lower bound are both sigma square or epsilon square. And for the upper bound, the sample mean estimator can achieve it well. Let's just design the estimator mu height n as the mean of the samples. Then by calculation, we just know that the expectation is mu and the variance is sigma square or n. So by Chebyshev's inequality, we know that the probability that our sample mean estimator is beyond the additive error epsilon. This probability is smaller than sigma square over n epsilon square. So at n in O sigma square or epsilon square, this sample mean estimator successfully carries out the mean estimation task. And the quantum computers can do this task better by using the amplitude estimation method. It can achieve tilde O sigma or epsilon quantum query complexity, which achieves the quadratic speed up. So, but this is only for the IID case. So what happens if those random samples they are still independent, but no, they are not identically distributed? So for this case, for the classical computer, the sample mean estimator still works. So by the same method, by the same calculation, we know that the expectation is still mu, and the variance is still sigma square bounded by sigma square over n. So by the same method, we know that the same upper bound sigma square over epsilon square still holds. But what about the quantum computers? So for quantum computers, the former method is not applicable because the non-identity, the amplitude estimation method can no longer be used directly. So for this setting, do we still have some quantum algorithm to achieve some quantum speed up, or is there some fundamental limits? So we will have some lower bounds. So this is what our paper just answered these questions. So let me talk about the problem formulation first. So for the quantum mean estimation problem, the standard input model is a quantum random variable, which is a pair HOX, where OX is a unitary operator which acts on the Hilbert space H, and it performs this mapping. It maps the zero quantum state to this quantum state. We can consider that when we measure the second register, it gives a result X with a probability APX. So this is exactly the distribution of the random variable, the classical random variable X. So to some degree, this quantum state can be seen as a generator, although it can be used for only once of this classical random variable. And we say that one query to this unitary OX is one quantum sample, and we say the number of the calls to this OX is the quantum query complexity. And in addition, generally, we cannot just get this distribution for free. Always it requires some calculation, so always we need another register for doing calculations or storing data and so on. So always we assume that there is some unknown garbage unit state for X here. And this is quantum random variable. And our quantum non-identical mean estimation problem is that given a sequence of quantum random variables OX1 to OXT, they have the same mean mu. And we are given another parameter, the repetition parameter M. It means that for each of those quantum random variables, those different quantum random variables, we can query them. For example, we query to some OXI, and this query can also be a query to OXI regular or some controlled version of them at most M times. So some query to each of those different quantum random variables at most M times. And our task is still estimate the mean mu with additive error epsilon with probability at least 2 over 3. So let's dig into a little deeper to these definitions. So in this quantum non-identical mean estimation problem, the only constraint we put on those random variables is only that they should have the same mean mu. However, the quantum random variable is unitary. It contains much information. So we will see that the non-identity of the quantum random variables means much more than classical random variables. First, the random variables include the probability distribution Px can be different as long as they have the same mean, and this is just the same as the classical random variables. Besides, since the quantum random variable are unitaries, instead of only a distribution, they still have some garbage state, and they can be also different. In addition, in this definition, we have only defined the act of OX on the zero state. So the whole complementary state of the zero subspace is not defined. So this is also a result of the non-identity. So we have these 3 different kinds of non-identity.
So what is the reason that include this garbage state?
So there are many ways to define the oracle, right? So there's also an oracle that can be defined just with this distribution Px on X. So my question for you is, why do you need this garbage state? Is there a particular reason?
So I guess the one reason is that this is a standard input model of quantum mean estimation problem. So many in the literature, many paper about such problems is as this input model. And I think one reason that people do this is that we study the mean estimation problem for application. Maybe we have some other problems, and it may call this mean estimation problem as a subroutine. And in this algorithm, we may construct some unitary to build this distribution. However, in this processing, we cannot just calculate this distribution for free. It always requires some calculation. So phi-x here is always for the calculation and for store some data and for other things. Okay, thank you. So this is a non-identity of the quantum random variables. And later we will see how we can overcome this non-identity to design some efficient quantum algorithms and how we utilize this non-identity to prove one lower bound. And now let's look through the results first. In this table, I only listed the results for Bernoulli random case, but some of the results can be generalized to a more general case. We note that for classical random variables, as long as the mean mu is fixed, the whole classical Bernoulli random variable is fixed. They cannot be non-identical. But for the quantum case, they can, because we still have other resources of the non-identity. So our results are listed here. If the repetition number m is in omega log 1 over epsilon, which means we can query each of the different quantum random variables, x1 to xt, for a few times, just a log factor. Then we have a upper bound quantum query complexity 1 over epsilon log 1 over epsilon. So in this case, we achieve a quadratic speeding up. It is just as an ID case, and it is near optimal up to some log factors. And this result can also be generalized to the sub-Gaussian case. We only have to replace all these ones here to the sub-Gaussian parameter k. So and for the m equals to 1 case, which means for those different quantum random variables, we are allowed to query each of them for only one time. In this case, we have a quantum lower bound, which is omega sigma square over epsilon square. I use omega square here because it can be generalized to the bounded variance case. So compared with the classical bound, we can see that for this m equals to 1 case, we can achieve no quantum speedup. In addition, we also have another quantum lower bound is for general m, which is omega 1 over epsilon m. So from this, we can conclude that for m is in O1, for constant m, if the occurrence epsilon is not very large and not very small, we can also achieve no quantum speedup. Okay, now let's take a closer look to the upper bound. So for the upper bound, we state this theorem for bounded variables. Since that's the sub-Gaussian case by function, it can be easily reduced to the bounded case. So assume that our non-identical quantum random variables are bounded in an interval LH, and we are allowed to query each one of those different quantum random variables for a few times for omega log h minus L over epsilon times. In this setting, we have a quantum upper bound, which is O h minus L over epsilon multiplying by a log factor, which achieves a quadratic speedup. So how to prove this? For the bounded variables, we first use the standard method of conditional rotations to encode the mean mu, the wanted mean mu, from the distribution to this amplitude. So obtaining this quantum state, as long as we can estimate this amplitude, we have an estimator for the mean mu. In this process, we can see that at the beginning, there are non-identity in the distribution and in the garbage state. However, after it, the non-identity in the distribution is transferred to the garbage state. But how to deal with this non-identity in the garbage state? It is impossible because since there is such a non-identity, we cannot apply the standard amplitude estimation method directly. So our solution is to use an computing trick. First, we start from the zero quantum state and we apply a unitary UI. UI is this unitary. And then we apply a C0 gate to copy the information of those 1 and 0 to a new register. And then we apply a UI dagger to uncompute this garbage state. So after this process, we obtain a unitary VI. When it is applied to the zero quantum state, we obtain this quantum state. It contains two components. The first component, it is totally clean. Here, it contains no non-identity and only the information of Q, which encodes our wanted mean mu. So this component can be used to estimate the mean. And the second part is totally a garbage, and it gathers all the non-identity in the quantum random variable. So, and in this garbage, the first two registers are orthogonal to the 0, 0. So the first and the second component are orthogonal. And since the amplitude of the first, the clean part, is more bounded by some constant, So O log 1 over epsilon cos to this Vi amplifies this clean part to norm 1 minus epsilon. And then this garbage part is narrowed to a very small norm, and it can be regarded as a small error. And we can just ignore it and directly apply the standard amplitude estimation. So this is for the upper bound. We just gather the non-identity first from the distribution to the garbage state, and then they are all gathered in this real garbage, and the norm of it is narrowed to a very small space, and then we finish the upper bound. Okay, now let's come to the lower bound. For the m equals to 1 case, which means we are allowed to query to those non-identical quantum random variables, each for only once, and we assume that we have only a very small working register. This is due to some technique reason. In this case, we have a quantum lower bound, which is omega sigma square or epsilon square, which means we cannot achieve any quantum speed up in this setting. So how to prove this? We can prove that this lower bound holds even for a simpler case, even for the OX1 to OXT, encodes the same random variable, the same classical random variable X. Even for the distribution is the same, and we still have the non-identity of the garbage state for Xi and the non-identity of the action of OXI on the complementary space. So consider any fixed quantum algorithm which starts from the 0 state and contains T queries. We can always assume that the qubits used in the algorithm is divided into two parts, the query register Q and the working register W. And each time when we want to apply a query, it is applied to the query register. This is reasonable since
I'm slightly confused about your notation. So you use XO X1 as the subscript, but now in the equation you use superscript bracket I. Are they the same?
Yeah. Okay. I know what you mean. So here I use OX1 to OXT, which means they encode different random variable X1 to XT. But in this setting, we will prove that the lower bound holds even for they encode the same random variable.
Oh, so later, you just change the garbage state to a different state, but the distribution are the same.
Yes.
Okay.
Okay, so let's come back to the to any fixed quantum random algorithm. So it can be described as this: a sequence of unitaries. We start from the 0 quantum state and then apply an arbitrary unitary U0, and then query OX1 or OX1 dagger to the query register, and then another arbitrary unitary, and so on. And finally, we get a final quantum state phi t, and the measurement of it gives the estimation result. So for any fixed quantum algorithm A, which means a fixed sequence of U0, U1 to UT, and a fixed A1 to AT, we want to find a hard instance OX1 to OXT. We want to find a hard instance to disrupt the performance of the quantum algorithm to lead to a worst possible outcome. So looking at the sequence, we may think that these OXI, they are unitaries, and we have only defined its action on the 0 quantum state, and the whole complementary space, the action of OXI is not defined. So this is a non-identity we may utilize. So we may utilize this to construct a hard instance to build a hard instance to prove the lower bound. So later we just concretize this intuition. We define the effective component. So we first define the phi begin and phi end quantum state. It may seem like a little complicated, but in fact, for OXT, for our xi here, we only know its act on the 0 state, and for any OXI dagger, we only know its action on this quantum state. So here we just use phi begin and phi end to express the both the case for OXT and OXT dagger, and we define a pi begin projector. It projects any quantum algorithm on the query register to the phi begin quantum state, which is the only state we know how OXTAT acts on it. So the effective component is defined as each time after we apply an arbitrary unitary, and when the query register, when the quantum state in the query register has become an arbitrary quantum state, we apply the projector to project it to the phi begin quantum state, the only one we know that how OXTAT acts on it. So this effective components are fixed despite of the non-identity of OXT, and they are the only fixed part, the only norm part, the only part we cannot manipulate along the processing. And we can prove that on the other side, on the one hand, they are the only components with positive contribution, and on the other hand, they can be prepared by a quantum algorithm with constant query depth. So such a quantum algorithm cannot provide quantum speed up for this non-identical mean estimation problem, and neither does any quantum algorithm. So this is a lower bound. This is we also have another lower bound for general M, and it does not require the small working register assumption. Okay, so let's make a conclusion. In this paper, we explore the non-identity of the quantum random variable, and we have 3 different types of non-identity, and we show that how we overcome the non-identity on the Gabriel state for the upper bound to design efficient algorithm, and we see that how we use the non-identity on the action of the complementary space to prove the lower bound. So this is our paper. And thank you for your attention. This is a QR code. If you are interested in more details, welcome to scan it. And for further communication or questions, welcome to contact me by email. So thank you.
Thanks, Shrey, for the nice talk. We have plenty of time for questions.
So what are some applications of this? In which situation do you want to, does someone want to, estimate mean of non-identical variables?
Oh yeah, you mean, does it have some application? Okay, I can see that why we want to explore this problem is because we were studying some problem from quantum reinforcement learning. So in that problem, we just start from some state and do some action and go to the next state. So at every step, we are on different states. So it may give different unitary operator, but they have something same. So in this problem is that we have some different oracles, but they contain some same thing. In the problem we studied, it is a mean. So this is why we studied this problem. But in that problem, in fact, it requires us to query those different random variables each for only one time. But in this study, we know that for this case, we only have a quantum lower bound.
Any other questions?
Yeah, I think my question related to what this person just asked. So normally there are different type of choice of your encoding oracle, right? And I think from your upper bound slides that I can see that why you need to include this garbage state, because you have to operate it on that garbage state in order for your upper bound technique to work. But if we consider other encoding oracle without this garbage state, have you thought about this?
You mean the case without the garbage state?
Yeah, without the garbage state, you just directly encode the distribution into the amplitude.
I guess. Okay, so we have a lower bound for the m equals to 1 case. So in this case, we can obtain no quantum speed up. But I think that in most of the quantum mean estimation method or quantum amplitude estimation method, it always requires one query to some oracle or some oracle and a pair of some oracle to O dagger. So the query to O and O dagger always appears in pair. So I guess the result may be if we have some constant. We have some constant repetition number. It may give some. It may give some quantum speed up for sufficiently small epsilon. So, but for constant m and epsilon not very small, we can achieve no quantum speed up.
Okay. Yeah, I think in general these are interesting question to see different powers in terms of this encoding oracle. So if you could come up with different upper and lower bound for this new oracle, and they are different from your this encoding oracle, then this provides another example that different encoding oracle has the power are different.
Yes,
Okay.
Thank you very much.
Any other questions? I do have one question. So, so if I understood correctly, your proof technique, your algorithm is like you do amplification and then you do followed by amplitude estimation. Is that correct? So a few years ago in the IDD case, there's a paper from Robin Kothari and Brian Dono in which they used Grover with complex phases to shave off their log factor. So it's basically like, do you think you could apply something like that and shave your log factor?
Oh.
So it's just like 1 over epsilon, not 1 epsilon log 1 epsilon.
Sorry. I think maybe I didn't fully understand your question. So you mean that this cited paper contains log factor, or can I? Yeah,
there's a follow. I think the paper came around the same time when they improved Aryan and Yassin's paper results. And so they're complex. If you go to your table, yeah, I guess in I think the first line, they have the complexity 1 over epsilon. The log is not there, and because they use a more complex technique that basically Grover with complex phases. So I was wondering if you could use that here and shave remove the log factor.
First, I think that this log factor is difficult to move out, but for the standard mean estimation problem, people have results without the log factor. So this paper is published in 2015, and in this paper it contains a log factor. But I remember that in this paper, it is just without the log factor. It uses very complex technique and some tricks to remove the log factor. I think it is.
I see. Okay, thank you. I think let's thank the speaker again. With that, we end the session. Thanks for coming. I'll have a break.
All right, let's get started. Welcome everyone. I'm Dakshita Khurana. I'm going to be chairing this session. The first talk is going to be about multipartite to tripartite reductions for LEU and SLOCC equivalences. This work is by Zili Chen, Joshua Grochow, Yuming Chao, Gang Tang, and Chuanqi Zhang. And Zili will give the talk.
Okay, so first let's have a quick look at the LCC definition for LCC. So here is an example for two-partite LCC. In the beginning, Alice and Bob share a entanglement, and they can have like multiple rounds of local operation and classical communication. In the end, they will get a new entanglement state, which is psi, and we say that phi is LCC convertible to psi. So if we have this protocol, and so LCC is a physically realizable protocol, but here this SLCC is more like a mathematical definition to use to classify quantum entanglement. So here everything is the same except for the last step, the pure state became a mixed state, and as long as this mixed state contains the state psi, we say that phi is SLCC convertible to psi. And notice that if we have a SLCC protocol transfer phi to psi, there is no guarantee that we have a SLCC protocol transfer psi back to phi. So here we have our definition for LCC equivalence. If two states are LCC equivalent, that these two states are interconvertible through the LCC protocol. Similarly, we can have this definition for SLCC equivalence, and also we also have other equivalences for the quantum state. So here, if we consider two d-partite pure states, and we say that they are LU equivalents, as long as we can find d unitary matrices act on psi locally, it will send psi to phi, and then we say that they are LU equivalents. And here is an example for equivalence. So here you can see that if we apply the X gate on the second bit of the GHZ, we can get the second state. And now if we relax the unitary matrices to general linear matrices, we can have a very similar definition, which is called LI equivalences. And here is an example where these two states are not LI equivalences, are not LI equivalent, because the tensor rank for GHZ state is 2, and the tensor rank for W state is 3. And by the invertible matrix, you cannot change the tensor rank of a state. And so first we have a theorem which is proved by dual without rank in 2000. So they prove that SLCC equivalence is equivalent to LI equivalence. And then there is a result proved by Bennett, Papascu, Rowling, Smalling, and Sepalia. They stated that if two states are LCC equivalent, then these two states are also LU equivalent. And it's well known that bipartite entanglement are completely classified. So under LCC equivalence and or SLCC equivalence. So for the LCC equivalence, it's characterized by the Smith coefficients, because LCC is equivalent to LU equivalence, and by applying unitary matrices on a matrix, you will not change the single value of a matrix. And SLCC is characterized by the Smith ranks. It's because by applying inverted matrix, you will not change the rank of a matrix. But it's proved by Verstraete, Dehaney, Moore, and Virtually that full qubit states already have infinite many SLCC equivalence class, and right now there is no complete characterization for multipartite LCC equivalence or SLCC equivalence are known, and it's in a survey written by Walter, Gross, and Isaac, they guess that a canonical theory of multipartite entanglement may not exist. And so right now today, our work is regarding whether determining two multipartite entanglement is hard or not. So first, there was a result proved by Zhangji, Li, and Chao. So they can reduce a multipartite entanglement to a two tuples of to the equivalence of two tuples of tripartite or beta-type state, and so our result actually reduced the multipartite equivalence problem to the tripartite equivalence problem. So here the first result is proved by Groch and Chao. They prove that determine two multipartite equivalence under LI under LI can be reduced to tripartite equivalence under LI. And our result shows that it's also hold for the local unitary equivalence. And so this is a reduction for our. This is the reduction we use to prove this. So first, we reduce the deep multipartite LU equivalence to an algebra isomorphism over unitary group, and then we reduce this algebra isomorphism to tripartite LU equivalence. So here, let me introduce the definition of algebra. So algebra contains it contains a vector space, and then it includes a bilinear map. So here you can think about this vector state as the set of all the elements in this in this algebra, and this bilinear map will map any two pairs of elements in this algebra to another elements in this algebra. So actually, for any algebra, you can encode this with a 3 tensor. So here is the 3 tensor, and you can think about divide this into a bunch of frontal slices, and which is AI up to AN, and then this bilinear map can be actually represented by this mapping. So for any pair of vector u and v, it will map to a vector where each entry is the product of u transpose AI and v. And so now we can have our definition for algebra isomorphism. Since an algebra can be encoded by 3 tensor, so we say that these two algebra are isomorphism if there exists. Oh, sorry, it should be P. There exists a matrix, general linear matrix P, such that it will act on this. It will apply on the tensor A, send it to B, and if you visualize it, it will be like that. So here is our tensor A, and you act P and P and P inverse on 3 directions of this tensor. It will send it to the tensor B. Yeah, and so here we denote the equation 1 by this notation. So if we so we call it as A and B are are algebra isomorphic under general linear group. And so based on this notation, we can have our algebra isomorphism based on the tensor of the tensor version. So first is the general linear group, the algebra isomorphism over general linear group. And since we want to study the algebra isomorphism under unitary group, so here is our second definition for the where the A and B are algebra over unitary group, because in the like we want to reduce LU equivalence to the algebra isomorphism over unitary group. And so here is the instance of the algebra we will use to prove it. It's called the path algebra for quiver. So path algebra for quiver is an algebra spanned by all the paths in the quiver. And the quiver is just a simple multigraph. So here is an example for the quiver. So you can see this is a quiver. And so first it contains a vertex set, V1 up to V5. And for each edge, we represent it by X under two indices. So the first indices indicate that which interval this edge is at. And the second index indicate the order of this edge in the corresponding interval. And the paths are generated from vertices and edges in the quiver by some relations, like those relations. I will give an example for the fourth relation. So the fourth relation is actually the relation between edges and edges. So here you can see that if we want to concatenate x22 and x31 together, we can get a length 2 path. Follow this rule. And but if we want to concatenate x22 and x41 together, we will get a 0 since they are not adjacent. And so here, or if we formalize the path algebra in the definition of the algebra, so first it will contain a vector space which is spanned by all the paths in this quiver, and then the bilinear map will be all the concatenation relations. And now we can actually associate any vector space, any tensor product of vector spaces with the following tensor. So here each interval will represent a supporting vector space, and there are D intervals. And so here you can see the number of paths, which is the dimension of this path algebra is bounded by this number. And we call the path algebra for this quiver as path Q. And now we can have an observation that for all the quantum state in this vector space, we can always map it to a length D path in this quiver by applying the same probability amplitude. And so after we have our path phi hat, we can use it to obtain the quotient path by phi hat, and we denote the three tensor encodes this quotient algebra as A sub phi. And we prove that if we determine two multipartite state, the LU equivalence for two multipartite states can be reduced to determine determine the algebra isomorphism over unitary group. And so right now it's the second step for our proof. Now we want to prove the algebra isomorphism to the tripartite LU equivalence. So if you let's recall the definition for the LU equivalence. So it's like that, and you can actually think of this as think of phi and percent as 2, 3 tensors, And this U1, U2, and U3 will act on the 3 direction of this 3 tensor. It will send phi to psi. And so this is actually a 3 tensor isomorphism over unitary group. So we will have this notation that A and U are unitary isomorphism for A and B in the U tensor weight tensor W. If as long as I can find 3 unitary matrices satisfy this equation. And so our reduction is inspired by the reduction for tensor system isomorphism to 3 tensor isomorphism proved by Fraterni, Grocho, and Sagaciuk. And because the tensor system is just a top of tensor, where the supporting vector space of different tensor may share this, may be the same vector space, or there might be some tensor that is supporting vector space may be the same. And so here we use their technique to prove that determine two 3 tensor are unitary isomorphism for A and B in U tensor W tensor W star can be reduced to 3 tensor are unitary isomorphic for A and B in U tensor weight tensor W. And finally, our result, like combining these 2 steps together, we can have our result reduce dipartite L equivalence to multipartite LU equivalence. And here the dimension below up is just polynomial bounded by the dimension of the previous dipartite quantum state. And so as you can see that our result is only work for pure state. So we might wonder if there is a same result which can reduce the multipartite equivalence to tripartite equivalence for the mixed state. Thank you.
Thanks for the great talk. Any questions?
Thanks for a very interesting talk. I was just wondering, like, can you give some intuition how one can see from converting from n-partite to 3? Is there some sort of non-trivial mapping? Because I mean, it's you're bunching stuff in a non-trivial way, or
yeah. So first, it's because for any vector space we can represent it with a positive algebra, right? And now it's just a positive algebra. It didn't encode any information for the quantum state. And now so here, this phi hat will encode some information for the state phi, right? And if we apply the quotient, path q divided by phi hat, now this path quotient algebra will encode some information for this quantum state. And now we actually prove that like there is a reduction that reduce the two multipartite state LU equivalent can be reduced to the isomorphism problem of this 2 quotient algebra. And since you can think of quotient algebra as a special type of 3 tensor, so now we reduce this problem from D rank to 3 rank. Yeah.
Okay, thanks. Another question. So, like for case separability or GME, that type of like different class of
what?
Like genuine multipartite entangled state, this kind of states, like, is it easy to see how you would translate into like relationship in the 3-partite case?
Yeah, I don't think it will. I think you can compute it, but it will be very tedious. Like you need to do a lot of calculation. Yeah.
Okay, so
Yeah,
no
but the
clear-
dimension blow up is just polynomial blow up.
Okay, yeah, thanks.
Thank you. Any other questions? Okay, let's thank the speaker again. Our next talk is PowerPoint. Okay, we'll start this next talk in about 5 minutes, just to maintain timings. All right, let's get started. This next talk is going to be about how pseudo-entanglement ain't cheap. This is a work of Daniel Liang, Sabi Grewal, Vishnu Iyer, and William Kretschmer. Daniel, please feel free to start.
Thanks for the introduction. Like Dakshita said, this is called Pseudo-Entanglement Ain't Cheap with my wonderful co-authors, Sabi Grewal, who is not here at the moment, but attending the conference, Vishnu Iyer, who's sitting in the audience right there, and William Kretschmer, who could not make it. So what is pseudo-entanglement? So it's a concept that was introduced by the set of authors quite recently. And basically the idea, this is not the formal definition, but I'll take two sets of quantum states, call it psi sub k and phi sub k. And we're going to say both states can be synthesized efficiently. And one has large entanglement and one has small entanglement. But you cannot computationally distinguish these two states. So I'll give you just like copies of one of these two sets of states. I promise you it's either psi k or phi k. And you can't tell which one it is, and yet somehow one has large entanglement and one has small entanglement. And the idea is that the small entanglement state is like pseudo-entangled. It seems like a highly entangled state, and yet it is not. And then the synthesized efficiently part is just, maybe it can be used for cryptographic means, similar to, say, a pseudo-random state, which I will introduce in a bit. I will note that there's an alternative definition of pseudo-entanglement introduced by these set of authors. I won't go into it. It's like slightly different, and we don't say anything about that. If you've heard of that, like we don't say anything about that. Okay, so cheap relative to what? So the idea of a pseudo-random state, if you've been to the plenaries, you've probably heard enough about this, but it was introduced by Ji, Liu, and Song in 2018. And it's a very similar idea as pseudo-entanglement, but now we only have one set of states, just called psi k. Psi k has to be able to be synthesized efficiently, and you can't distinguish it from a Haar random state now. So rather than two sets of states you can't distinguish, you just distinguish it from a very naturally random state. And the focus of this talk is constructing pseudo-entanglement easier than constructing pseudo-random states? Pseudo-random states are, as you went to Tomoyuki's talk, useful for a wide variety of things. And the idea is, can you somehow show that pseudo-entanglement might be easier than the other? We currently, unlike the graph that he showed, we don't have, I think there's actually recent work, but we don't really have good relationships between the two classes. I think we now have something about the alternative definition of pseudo-entanglement and EFI pairs coming out of Okinawa, but this definition that was introduced by Boland et al., I don't think there's actually any formal relationships. So the question is, can we somehow show that one is easier than the other? And so what was already known, so both can be constructed using one-way functions. And for the lower bounds, really not too much. This isn't too surprising. If you could show that they didn't exist, then you would show that one-way functions don't exist. We don't expect to do that. But something that we can show is that pseudo-random states require a linear number of non-Clifford gates. So if, let's say you're in the Clifford plus T basis, then you need at least a linear number of non-Clifford gates to create a pseudo-random state. And the point of this work is to show that the same lower bound holds for non-Clifford gates for pseudo-entanglement. So at least in terms of the Clifford plus T basis, you currently don't expect to be able to produce pseudo-entanglement using less non-Cliffordness as a resource than pseudo-random states. Does that make sense to everyone? Okay. So what are non-Clifford gates and why do we care? This should be reviewed for most of you, but the Clifford set, the Clifford gates are the following set of unitaries. You've probably seen the Hadamard and CNOT. You've definitely seen those. You probably have seen the phase gate. And a non-Clifford gate is anything that is not generated by the set of unitaries. The classical example is the T gate, which is the following. It's not actually that important to know the details of it, but just know that every time you apply a non-Clifford gate, it adds complexity to the stabilizer states. By adding just a singular non-Clifford gate, you can create a universal gate set. So basically, every time you add non-Clifford gates, you add like complexity and like the amount of expressibility you have. This is also related to things like magic state factories and fault-tolerant computation. And the original reason we were looking at this problem is that there was thought to be a relationship with ADS-CFT. So Tony Metger approached us with this problem. It turns out that both the conjecture that they had and the relationship that they were thinking about are not true, but we thank them nevertheless for giving us this problem. Okay, so what's the main idea? So if you know things about learning stabilizer states, you might know that in 2017, Montanaro gave this algorithm to find the description of an unknown stabilizer state, given copies of the state. If you don't know what a stabilizer state is, it's basically a state produced by 0 non-Clifford gates. And that's the following runtimes. It's not so important. And then there was another very old result that says, given the description of a stabilizer state, you can compute its entanglement exactly across any cut. So in the first part, you can get the description. In the second part, given the description, you can find out the entanglement across any set of qubits. So the algorithm is pretty straightforward. And the idea is basically as follows. Or you can think about it like this. There's a set of local Clifford operations you can apply across the cut. So let's say Alice and Bob each apply a Clifford circuit. And what you end up getting is this state that looks like this. So you have a phi A and phi B that are unentangled from Alice and Bob. And you have this shared phi AB, and it turns out to be maximally entangled. It has to basically be a Bell pair across every qubit in phi in those shared registers. And this is a maximally entangled state, and you can get the entanglement from that directly, just by counting how many qubits you have. And basically, the improvements that we show is that, one, there is a previous result that given a state that's produced by a bounded number of non-Clifford gates, that you could find what's called like the stabilizer information, so to speak. So you don't get a complete description of the state, but you get some important information related to stabilizer states. Another thing that you can do is you can find an approximation of the entanglement given this stabilizer information. So basically, it's sort of generalizing those previous results we saw to when you apply some amount of non-Cliffordness to it. And I'll basically go into detail on how we generalize that. But the main idea that you want to take away is that we have a similar picture now to before. We have these local Clifford unitaries, and now we have this shared psi AB, where we basically just don't know what that state is. It could be maximally entangled, it could be completely unentangled. We basically just punt on those qubits and say that that's basically where this K error comes from. And the rest of the registers look exactly the same. We know exactly what the entanglement is for those qubits. So the high-level idea is that every time you apply a Clifford gate, or non-Clifford gate, I should say, you lose one bit of information about your state, and that just creates the error that we see. Okay, so what exactly is stabilizer information? So hopefully this is also a review for you, but there are these matrices called the Pauli matrices. So a Pauli matrix stabilizes a state if it's a one eigenvector or eigenstate of that Pauli matrix. And you can think about this as a set of constraints. So if I define stab of psi to be the Pauli matrices such that the Pauli matrix is stabilizes that state, it sort of constrains your state in a certain number of ways because it has to be like an eigenvector. So if you have a ton of constraints, the maximal number is 2 to the n, then you completely constrain your state, and we call that a stabilizer state. And basically, every non-Clifford gate you apply reduces or can reduce the number of constraints you have by this explicit amount. But basically, because we're reducing the number of constraints, that's why there ends up being a larger and larger register qubit or set of qubits that we just don't know anything about. But it does so basically in a very natural way, which is why we can still make progress. So here's an example of how this works. So let's say I say this Pauli matrix ZIIIII is a stabilizer of psi, then psi has to take the following form. So basically, if you take ZIIII and you multiply it by state psi, this creates a constraint on your state. I claim that this constraint is satisfied by any state with the following. Do I have oh, I do. Yeah, so basically it has to be 0 in the first qubit and then some arbitrary state over here. Similarly, if I have XIIII, then it has to be a plus state on the first qubit followed by some arbitrary state. So that's an example of like how these constraints work. You can do a similar thing with like the last qubit, for instance. So these are like very simple examples, and they demonstrate actually how we can show that certain qubits are unentangled. So for instance, if this qubit is unentangled with this psi prime over here. A more complicated example would be, let's say that XII, XII, and ZII, ZII are both stabilizers of your state. Then I claim that the first and fourth qubit must form an EPR pair. This is probably hard to see if you're not familiar with stabilizer states and things like that. But this is more or less like how the result of Fatal et al. That I cited way back from 2004 works. Another example would be this set of stabilizers, or this set of Pauli matrices as stabilizers means that the first and the sixth qubit form like this maximally entangled state. So that's just to gain some intuition about how this all works. So what is the main theorem? So let A and B be the number of qubits that Alice and Bob have. And let stab sub A be the subset, sorry for the notation, by the way. Let stab sub A be the subset of stab psi. So stab psi is the set of stabilizers of your state that only act on Alice's qubits. So for instance, if the first 3 qubits are Alice's, then ZII and XII would be like in stab sub Alice. And let's say, and these guys would be in Bob's because it only acts non-trivially on the last 3 qubits. And then let's say these guys would not be in either of these sets because they act non-trivially on both the first and the last 3 qubits. Okay. So with that out of the way, let me just say that these things can be found efficiently, and that will be important for our algorithm. But the idea is that the entanglement, so basically like the von Neumann entropy of the reduced density matrix, I hope that's all familiar for you guys, but it's basically upper and lower bounded by these 2 quantities. So the number of qubits minus basically the number of things in this set, stabs of A. So the bound might be somewhat esoteric. I'll explain more about how we get the actual result we want later. And I'll just give a shout out to Gu, Olivero, and Leone. I think they're in the audience, or at least I think Lorenzo's over there. They have a similar result, and I think they have a different proof, so check it out. So anyway, the point is that if I take the upper and lower bounds and I subtract the upper from the lower, this is basically just how much error is in our bounds. And it turns out, you just do some quick algebra, you get this quantity. And if you recall that I showed you way back that the number of non-Clifford gates implies a lower bound on this quantity right here. So if you plug that in, you just end up with a bound of 2K. And naturally, you'll just output the thing in the middle of your bounds as your estimate. So upper minus lower divided by 2, the arithmetic mean. And therefore, if you just do that, then you're going to be within K always of the true entanglement. So that's how we get our K approximate error. I mentioned before that we only approximately learn this so-called stabilizer information. Turns out it's not a big deal. So formally, we learn the stabilizer information of a state that is close to the true state that we have. And then there's a result by Fan and Odenart that shows that if your state is close, then the entanglement is close. This is like the actual quantitative bounds that you get. And so what ends up happening, I'll give you the actual details, is so to learn entanglement to error k of a state produced by like at most k non-Clifford gates, you can learn it to error k plus O of epsilon n in this many samples and this much time. So like a linear in n number of samples and a cubic amount of time. The cube just comes from the Gaussian elimination process I talked about earlier. Otherwise, it's under certain regimes, you could probably find it faster using like some fast matrix multiplication algorithm. But that's just why I brought it up. And I just want to add at the very end that there's sort of a clever trick that we use to get rid of all the error besides the inherent error from not knowing what those qubits are about. So we basically get rid of the this epsilon n part. And now the number of samples is n cubed and the time is n to the fifth. And basically the idea is that there's two sources of error and they cannot be satisfied simultaneously. So this is not actually how it works, but this is the way you should think about it, is that there's like an inherent k-1 error in the worst case. And then there's either a +1 error from like the inherent from going back from this step. So there's either like a +1 error from this step, or there's this O of epsilon n error we get from only learning the information approximately, but they both can't happen at the same time. So what ends up happening is that if you set epsilon to be O of 1 over n, then both of these are just +1, give or take. So k-1 + 1, you just get k. So yeah, so basically we can, like I said, get rid of this plus O of epsilon n error by just doing some clever parameter counting and knowing that these bounds are not saturated at the same time. So what are the conclusions? We can estimate the entanglement of states produced by some not too many Clifford gates, like a linear number, basically. And the corollary of this is that around omega k non-Clifford gates are needed to create an entanglement gap of k. If you recall, we were originally trying to figure out how many non-Clifford gates we need to create pseudo entanglement, and the largest amount of pseudo entanglement you can create is linear. So yeah, when the maximal entanglement gap is linear, then this matches the pseudo-random state lower bound, which is the goal. And also, this is tight up to polylogarithmic factors. So if you assume the existence of linear time quantum secure one-way functions, then Fermi-Ma has an upcoming result that can produce pseudo entanglement states in like linear times polylog time. So this is tight, and this you might be wondering about this assumption. I guess the point is that we might not, this might not be like the best assumption to rely on, but the idea is that if you could improve our result, then this would discredit the existence of linear time quantum secure one-way functions, and we don't expect our techniques to be able to do such a thing, because why would stabilizer states and things like that disprove such a strong, statement? And I was told I should do this, but I'll be on the job market soon, looking for a PhD, a postdoc, or a faculty position. So this is my contact info, and thank you. Yeah.
So great talk. Thank you. Any questions from the audience?
So yeah, this result only works for pure states, I guess, right? Because I think David and Manuel, they consider something more general that's mixed states that are pseudo entangled.
Yes, I think the Bolin et al. Result is only for pure states as well. So we only looked at pure states as well.
Other questions? We have a bit of time, so while you think about any questions you may have, let me ask a couple of questions. So you said something about pseudo entanglement relating to quantum cryptographic primitives like EFI pairs and commitments.
Okay.
Could you said that there was maybe some recent results showing something like that?
Yeah, I mean, maybe the authors are here, but I think this is not the Bolin et al. Definition from what I recall. There's the other definition from Arnon, Friedman, and Vidic.
Would you, what is the other definition? Like, how does it differ from that?
Right. Okay, so the one difference is that only, I believe, the small entanglement state has to be prepared efficiently. And also, the entanglement is only over a fixed cut, but now the what the definition of entanglement changes. So in this ABV definition, the low entanglement state has to be prepared using a small number of bell pairs. So it's like the synthesis cost of entanglement. And the high entanglement state has to have, you need to be able to synthesize a lot of bell pairs from that state. So given copies of that state, can you create, how many bell pairs can you create out of it? So yeah, the difference
These are
is
not known to be equal. It feels like they should maybe be, it seems similar to me, but
that might be a new paper for you. Anyways, I think the result says that pseudo entanglement implies, or EFI pairs implies pseudo entanglement of this ABV kind. So it says that that kind of pseudo entanglement has to exist if EFI pairs also exist, and EFI pairs have to exist if all the other pseudo random states exist and things like that. So I don't know necessarily if that definition of a pseudo entanglement implies all the things like bit commitment and things like that. But the point is that it's like some baseline assumption that you can make.
okay, so follow-up question. Does your result say something about the complexity of synthesizing cryptographically useful primitives like commitments?
Not that I'm aware of, unfortunately. Yeah.
That's another paper for you.
Yeah.
Any other questions? Okay, let's thank the speaker again. I believe we're running ahead of schedule, so we'll start the next talk in 10 minutes. 12 minutes to be precise. We'll start at 4. Okay, so the next talk is going to be about a computational Sirelson's theorem for the value of compiled XOR games. This is a work of David Chui, Giulio Malavolta, Arthur Mehta, Anand Natarajan, Connor Paddock, Simon Schmidt, Michael Walter, and Tina Zhang. And Simon will give the talk.
Exactly, yes. Well, so thanks so much for the introduction. So yeah, as you already heard, we will talk about some computational Sirelson theorem for the value of compiled XOR games. And XOR games are non-local games, and then compiled non-local games. So we have some compilation procedure for non-local games, and then the Sirelson theorem will just be some upper bound of the winning probability for the compiled XOR games. Okay. So what is a non-local game? So in a non-local game, we have two players and a referee, and the players, they get some questions from some question sets, and they have to answer with A and B from some answer sets. And once they received their questions A and B, they are not allowed to communicate anymore. And for each non-local game, there's a verification function, so a function with values in 0 and 1, and the players win if and only if this function is actually equal to 1. And so the idea is, so in a non-local game, the players should be very far apart, so they cannot communicate. And the goal of the players is to actually maximize the winning probability. So this is this omega, where pi is the distribution. So the probability of the referee sending X to Alice and Y to Bob. Then V is this verification function, and P is the probability of Alice and Bob getting X and Y and answering with A and B. And where does this probability distribution, so this P, comes from? So before the game, they are allowed to agree on some strategy, and then depending on this strategy, one gets this probability distribution. And one way to model such strategies in the case of when the two players share some entangled state is that so we have some state in some tensor product Hilbert space, and then Alice and Bob are allowed to do local measurements on their local Hilbert space. So those are just positive operator valued measures. So I have some positive operators that sum up to identity. And then the correlation we get, so the probability of Alice and Bob receiving X and Y and answering with A and B is really, so I have the state, and in there I have the measurement operators in the tensor product. Okay, so this is a non-local game. So what is the compilation we do for such a non-local game? So the general idea is that, okay, in a non-local game, the players are so far apart that they cannot communicate. And now, instead of having this locality assumption, we want to put some crypto assumption. And this should guarantee some similar assumption as the non-locality. And for this, we use a QHE scheme. So we have some algorithms, gen, eng, eval, and dec, and lambda is some security parameter. And now the game is not simultaneous measurements with Alice and Bob, but we just have one player. And in the beginning of the protocol, so the verifier, he first uses gen to get some secret key. Then he uses pi, so the same one as he used in the non-local game, to sample questions for Alice and Bob. And now he uses an encryption, so he actually encrypts the first question, sends it to the prover, and the prover now has to answer also in an encrypted fashion. So this is basically to ensure that, okay, it's a sequential game, but in the first round, the player or the prover doesn't know which question he got or what he answered, in a sense. So in the second round, he has no information about the first thing. So it's very similar to, I have two parties and one of them answers with something, but I don't know what the question was or what the answer was. And Now in the second round, so we had a first encrypted round, but the second one is now really in the plain text. So we have the same question as in the non-local game, and also the answer set in the non-local game is the same. And then the players win if, so we now decrypt the alpha, so the first answer of the prover, with the same secret key, and then we want that the verification function of the non-local game is 1. So we just win in a similar way. Okay, and now what do we get as a correlation? So okay, we get a lot of sums or expectations for the secret key and encryption and decryption, but essentially it's like a sequential measurement. So we have some state, we apply measurement operators, and then in the middle we get the POVM. Okay. So what are the properties of my QHE scheme? So all of the algorithms are actually QPT algorithms. So for Gen, I have some security parameter lambda where I get some secret key. Also for ENC, I take the secret key and the message and get some ciphertext. The decoding or the decryption does exactly the same. So I take some, or the reverse, I take some secret key and the ciphertext and get some message back. And eval, so as you saw in the protocol, there was no eval, but I somehow want to, so if I have a strategy for a non-local game, I actually want to translate it to the compiled game. And this is what eval is for. So if I have some tensor product state and some measurements, then I can use eval just on the first part of the, let's say, A Hilbert space to actually work with the encrypted answer to do honest quantum. So if I have an honest quantum strategy, I can use it in the non-local game. Okay, and what are the things we want to do? So, or we want that the compiled games actually do what we want. So the first thing is this correctness with auxiliary output, which is exactly what I said. So this eval should be in a way so I can use it to transfer non-local strategies to the compiled game with a similar winning probability. And then I also want to be secure against quantum distinguishers, so there should not be any QPT algorithm that can distinguish the encryption of two fixed messages. Okay, and from the second part, we actually get some, so we had this correlation or probability distribution. And for from the QHE scheme, we actually get some non-signaling condition for this probability distribution. And maybe to remind you, what does non-signaling mean for probability distribution? It's really that, so if I sum over A, then this should be independent of the question of Alice. So basically, if you look at this in the non-local setting, then this means that the questions and answers shouldn't depend on the questions of Alice. So Bob answers B independent of what Alice got, which makes sense because you shouldn't know this. Okay, and now, okay, so the first part is just rewriting the probability distribution for the compiled strategy in a more nice way with this trace and some normalized state and some so the Bob operators. But then what we actually get is, so we have this non-signaling property, which is really the same as before, but now we can actually take polynomials in the operators of Bob, not just the Bob operators. So usual non-signaling would just be, I have those BYBs, I can put them in there, and then this sum over the trace would be the up to negligible for x1 and x2, but now we have the same even for all polynomials in the Bob operators. Okay, that's very nice. So let's see again what are the differences of quantum strategies for non-local games and compiled games. So for non-local games, I rather have some tensor product Hilbert space. I can do some local measurements. Now I just have one Hilbert space. I'm just one player, but I can do sequential measurements, and I have this very strong non-signaling condition that is based on the assumptions on QHE. And then Okay, also non-local games are purely information theoretic, so there's no computational assumption. And for the compiled games, our strategies should be QPT algorithms. So it makes sense to use the QHE scheme. Okay, and then, yeah, as we saw before, so for the probability distributions, for one of them, we get this tensor product Hilbert space, and the other one, we actually get the trace of some sequential measurement. Okay, so what do we know? So I should say, so this compiler was already known from Kalai et al. And they already worked on the classical. So what can I do with classical strategies for compiled games? They also had something for the quantum strategies, but let's begin with the classical strategies. So what I show is that if I take a non-local game, I use this compilation procedure, then for every classical strategy for the non-local game, I can also find a classical strategy for the compiled game that has at least the same winning probability up to a negligible function. And then, okay, so this is nice. I can basically compile every classical strategy, but what the second part says that, okay, I can actually not do more. So if I have a classical strategy, any classical strategy, then I can also not be better than any classical strategy for a non-local game up to some negligible function. Okay, so this is the classical value. So there everything's nice. And similarly for the quantum value, so we had this eval, and what this eval does is exactly what this theorem tells you. So for each quantum strategy for a non-local game, I can also find a quantum strategy for the compiled game with a similar winning probability. So I have the same winning probability as a non-local strategy up to some negligible function. And then, of course, we ask now, so can we also bound the quantum strategy or the quantum value? So do we know if I have a quantum strategy for a compiled game, it cannot do better than any non-local strategy? And so what we did is we proved this in the case of XOR games. So what are XOR games? So it's a non-local game. And the feature of XOR games is that the answers for Alice and Bob are just bits. And also that there exists a function on the questions of the referee. And then, based on this function, the players win, or winning only depends on the XOR of the answers. So I just have bits, I can use it, look at their XOR, and then depending on the value of the function, they either win or lose. Okay, and one example, which is, I guess, the most famous non-local game, is the CHSH game where the questions and the answers are bits. And then I win if the product of the questions is the same as the XOR of the answers. So my G will just be X times Y. Okay, and the very nice thing about XOR games is that the quantum value, so the maximal winning probability for XOR games, is actually given by the so-called vector strategies. So I don't have to maximize over all non-local strategies or quantum strategies, but I can really look at vectors in RD and maximize over all those vectors, which is way easier than doing this for quantum strategies. Okay, so what's our result? As I said, so we take some XOR game, and then we can show that every quantum strategy for the compiled game has winning probability at most quantum value of the game plus some negligible function. And so we actually have two approaches to the proof. And the important thing is really that we have this vector strategy bound, or we can say, okay, the optimal quantum value is actually achieved by some vectors, because in the first approach, we call it macroscopic locality approach, which sounds fancy, but in the end, we really just bound the winning probability of any quantum strategy with some chain of inequalities, and then by some vector strategy,
And then since we know that those vector strategies are an upper bound, we also get that this is at most the quantum value. And what we use here is just Jensen's inequality and this very strong non-signaling condition from the QHE scheme. Then instead of directly working with the winning probability, one can also look at the sums of squares approach and remember that. So knowing that the quantum winning or the quantum value being the same as the value of the vector strategies is actually just the same as knowing that the quantum value will be achieved by the level 1 of the NPA hierarchy. So what one can just do is one finds some nice SOS decomposition and then define some pseudo expectation, show that it has some nice properties. And then, so this is basically, both of them are in the same picture, just one looks at them in a different way. Okay, and then we also have some additional results. So we can also show that the quantum value for parallel repetition of XOR games is preserved. So parallel repetition just means that I don't just send one question to Alice, one to Bob, but I'm setting 2 questions or 3 at the same time. They have to answer with 3 of them, and then they win the game if they win all of them at the same time. And we also get some self-testing results. So maybe you ask, okay, well, why is it good to bound the winning probability for such compiled games? Well, so it's always good to know upper bounds, because then you know when you have an optimal strategy. And self-testing only works if you know that your strategy is optimal, because then you're somehow some extreme point in some convex set, which you don't know if you don't have this upper bound. And then, what we can show is that, so for some of the XOR games, we get anti-commutation relations for Bob's observables. And similarly, we can also get self-testing results for the Magic Square game. So the Magic Square game is not an XOR game, but it's one of the more famous games. And the good thing is that the Magic Square game has winning probability 1. So in some protocols, it's nice to actually have a game, where one can always win with quantum strategies. Okay, so very good. What is so maybe I give some summary and some outlook. So what did we do? So we had this, start with non-local games. We compile, we have this compilation procedure, and then we can show that actually for XOR games, basically everything is preserved. So we know from before that the classical strategies cannot do better than the classical non-local or strategies of the non-local game. The same is true for the quantum strategies. And then we also get some self-testing results in the sense of anti-commuting observables for Bob. And one can use such self-testing results to get a protocol for classical verification of quantum computation, which was already done by Anand and Tina. And maybe just to say that this work is around. So last month we were actually able to show that the quantum value is actually, so for compiled games or 2-player compiled games, is actually bounded by the commuting operator value. So that's quite nice. And that's everything I wanted to say. Thank you.
Okay, any questions?
So like in the regular setting, self-testing results, they are like robust, right?
Mm-hmm.
I mean, there's order root epsilon robustness. So do you get similar robustness statement here?
Yes. So in the crypto setting, you always have this negligible function around, right? So there's no exact self-testing in a sense. So all of this will be robust. So you can take epsilon perfect strategies and then get some.
So like order root epsilon plus some negligible function.
Yeah.
Okay. And there were some like other self-testing results like without doing this compilation, I think by Vidik and others in the past, right?
There are more self-testing results, yes.
Yeah.
So-
So just trying to see I mean, if you can say which one gives better guarantee or something.
Yeah, I mean, in principle, so there are self-tests for, let's say, all bipartite entangled states, things like that. But it's not clear if one can compile all of those or if it makes sense all the time. Yeah, because somehow here the problem is that we mostly, so self-testing here is rather about, let's say, algebraic relations of Bob's observables, because we don't really have a bipartite state because we just have one Hilbert space, right? So this is rather, we just look at Bob's observables because Alice's are encrypted, and then Bob's observables will anti-commute, which is good enough to, for example, get a qubit, but we don't really know the whole structure of the states, for example.
Thank you. Yes.
Thanks for the nice talk. So you are changing these non-local games to some compile games. So then you are showing the upper bound for quantum strategy. So now, what will happen? Let's say you are taking some PR box, pop-up scroll box.
Sorry, say it again.
A PR box. Like if it is no signaling correlation, then can you also upper bound or like the non-local games also achieve some? Can it achieve the bound one?
I mean, I would say that the guarantees we get from the QHE scheme are stronger than PR box. So PR box is like non-signaling. So I can win CHSH with PR box, right? And this I shouldn't be able to do here, but maybe there are some other. So maybe there are some other assumptions where one can do something.
Yeah, but you cannot use SOS or other. The sum of square decomposition you cannot use. I mean, I don't know how to proceed with, let's say, for PR box, whether there will be some bound, whether you can calculate some bound there.
Yeah, I'm not sure.
Yes, so I was wondering if you can use this compiler for the multiple resetting that's more than two prover. Like, are there any attempts on that?
Yes. So the original protocol is also done for K players. So the idea is that you don't just encrypt the first round, but so you will have K sequential rounds, and you encrypt everything but the last one. And the QHE scheme should be good enough to say that I can compile all quantum strategies, but for upper bounds, I'm not sure if there's any work yet.
So do you have any similar results on XOR games like the multiple resetting?
No, we don't.
Okay, I see.
I have two questions. So first, for the Hilbert space that you consider for the compiled XOR games is always finite dimensional. This is by okay. And the second one, is there a possible way formulation of the result as a tensor norm in the tensor norm context or not?
What do you mean?
The classical value of the game of this compiled XOR game or the quantum one, is there a way to rewrite it as a tensor norm in a tensor norm formalism, like in standard XOR games? So you have the classical value of the game, and the quantum one is given by the some norm associated to the game that characterizes the game itself. So I don't know if there is a way to write the classical and the quantum value of this compiled XOR game as a tensor norm. No?
I mean, in a sense, the values are the same. So if you can write the non-local ones in some tensor norm, then okay, the values maybe yes, but I'm not sure if there's some nice way from the compiled strategies to do this.
Okay, thanks.
I have a sort of follow-up question to something someone asked. So if you have a K-prover system, you said that there is a natural compiled game that takes K rounds. There is also another game that takes just a single round, where you simultaneously encrypt the queries to all provers and send them to the single prover, and then the prover simultaneously answers. Of course, this is a trickier non-signaling setting because now you have interactions between all possible pairs, and you don't have causality to help you. And so, is anything known about this setting where you compile like k prover messages into send it to a single one prover in encrypted format in just a single round simultaneously?
Okay, I'm not sure if this is the answer, but I thought there's some work that it's upper bounded by the non-signaling value then, because you have some spooky encryption
interactions, and they can simulate. So, but they can simulate all no signaling attacks. Is that
for all games? I'm not sure.
For certain
but
games.
Let's say for CHSH.
Okay, thank you. Any other questions? Okay, let's thank the speaker then.
It's already downloaded, I think. Yeah. Yeah, no problem. Just checking that everything works. I should be here. Tillage, so it's okay. Shayu, it's more complicated, yes. I understand. Like 2O. Yeah, it's a French name.
All right. So the last talk of this session is on the quantum decoding problem. This is work by André Chelou and Jean-Pierre Tillich, and Jean-Pierre will give the talk.
Okay, so before I'm going to explain the problem I'm interested in, so it's a quantum decoding problem. I will talk about a much more known actually problem, which is a classical decoding problem. And then I will explain actually how a classical decoding problem is related to a quantum decoding problem and why we were interested in this and what were the results. So classical decoding problem, you start with, let's say, a finite field over Q elements, call it FQ. You take vectors of length n over FQ, this forms a vector space, and now you choose a subspace here of the whole space, dimension n, and this is a linear code you're interested to decode. Okay, this is the first choice, and then you pick up a random element in this subspace here, C, and you add some error E to it, and this E is chosen according to some probability distribution, which basically favors elements of some which are rather small according to some metric. I'm going to talk about later on, but for right now, you can think of that E is rather small. And you give away the noisy code word, which is this sum C plus E. And now you are asked to find C, just from the knowledge of C plus E and the knowledge of the code. Okay, this is a classical decoding problem. It turns out that even for very simple cases where basically here the linear code is of dimension n over 2, let's say, and choose a rather natural error distribution, this problem is extremely hard. Basically, for natural choices here of error distribution, the best algorithm for solving it classically are exponential here in n. And also the best quantum algorithm for doing is exponential. And actually most of code-based crypto and most of lattice-based crypto, because lattice-based crypto, this is also the LWE problem here. It's chosen just a discrete Gaussian here for E, and it's extremely hard. And actually all this code-based and lattice-based crypto is based on the difficulty of this problem. Okay, now let's look at a related problem which could be viewed in some sense as a quantum version of this problem. So instead of giving this C plus E, what I'm going to do, I look at, for a given C, I look at all possible noisy versions of this C, or this C plus E, and take a quantum superposition here over all possible noise here, value here, and I take the amplitude here in such a way, if I measure this state, I get the C plus E exactly with the right probability here. So, of course, this means actually that the quantum problem here is not harder than the classical problem just because I can measure the states I have and solve it classically. But this quantum problem might be much easier. And now you may wonder, why do I care about this problem? Well, it turns out that some authors played this game 2 years ago, and they look at a very specific error distribution, and basically they found an algorithm, a quantum algorithm for solving this problem in polynomial time. And then by using Gregor's reduction, basically they were able to solve what is called the cis problem in a very, very specific region. So what is the cis problem? Basically, it's this. You choose again a linear code, and you choose some metric. In that case, they choose the infinite metric here. I'm going to be interested here in the Hamming metric. Hamming metric is just actually the distance between two vectors, x and y, is just the number of coordinates in which x and y they differ. So they were able actually by solving this problem this decoding problem in polynomial time to be able to find low weight code words in this code here according to the infinite metric. I'm interested in right now in the Hamming metric, and basically this problem is also very hard. It's, well, not in the whole regime. So for instance, if you take a relative distance in the Hamming metric, which is q minus 1 over q, where q is the size of the alphabet, the problem is easy. How do you do this? You choose just a random element here in this, and you expect actually what a fraction 1 over q of the coordinates which are equal to 0. So you find a relative weight of q minus 1 over q. Easy. Can you do better? Yes, you can use the fact that the code space actually is a linear space. So you may just want to find code words which are equal to 0 at certain position. How many positions can you choose? Basically, the dimension of the space. And this explains actually here the point that we have here, where basically you choose as many positions as the dimension allows you to do. And you have a very simple classical algorithm for doing this, and it turns out if you want to go beyond this, there is no polynomial time algorithm which is known. Actually, all the algorithms for go beyond this are exponential again. And then there is a part here where basically you can do nothing. Why can you do nothing? Just because there are no code words of this relative weight which are in this region here. So it's a classical problem, which is also very hard, and also crypto is based on the difficulty of this problem. And we may try to understand if these two problems are related. Actually, there are three problems right now because there's still this quantum decoding problem. And actually, there is a very nice reading the problem here of finding low weight code words to a problem of classical decoding, which is due to Regev. And it's a quantum reduction. It's a very funny reduction because the first problem basically has only one solution. And for the second problem, basically we are in a regime where there is an exponential number of solutions. So it's kind of non-intuitive, but you are able actually to get a reduction from one problem to the other. And the only known reduction right now actually goes through this quantum reduction. So how do you reduce one problem to the other? Suppose that you have an algorithm here for solving the classical decoding problem. And so what you do here, you first set up here this superposition over all possible code words in your code and all possible errors you are interested in actually in decoding. And then you add this register to this one here and get this. And now if you have something like this, if you're able to solve a classical decoding problem, it means that if you know C plus E, you can find back C. But if you can find back C, you can subtract C to this thing and get a 0 here. And if you look at a little bit at the state you just created, actually it's this state which is here. So it's this quantum superposition here. Forget about the 0 here because you can tensor it out. And you have this. And this state has some periodicity condition. If you look at what's going on actually at here for our y value here, it's the same amplitude as you have at the vector y plus c. So this because just you have a subspace here. So you have some periodicity condition, and so it's not. You can expect that you take the quantum Fourier transform of this, there will be something going on. Precisely what's going on actually here, you get a state which is only supporting the dual code. What is the dual code is a set of vectors which are orthogonal to all elements here of the previous code. So you get a nice superposition here of dual code words. And somehow, if you go back to Regev's algorithm, what you expect here, you expect if you measure something like this, if this F here is supported on small weight code or small weights here, you also probably expect this quantum Fourier transform also to be supported in some set, small sets. And so basically you have a way actually of sample small weight code words. So if you can solve a classical decoding problem, you can do this. But unfortunately, there is no good way of solving it classically. All, as I said, all the algorithms for doing classically have exponential complexity. But now if you look really what we have at this point here, actually we are missing something here. If you can rewrite this as a superposition over all possible code words, and the psi of C here is just the sum of f of E C plus E. It's precisely the one what we had for the quantum decoding problem. And if you expect actually that the quantum decoding problem is easier, well, solve the quantum decoding problem instead. And so basically you have a way here through this reduction to construct small weight code word by solving the quantum decoding problem. Great. So basically here, this is what we are going to do. So just to look at an example here, where you get something already non-trivial, look at what the alphabet is binary. And now look at the error model where basically I choose an error 1 in 1 bit with probability P. So this is binary symmetric channel somehow in coding theory. And so I get this probability distribution here on the error, where here this E here is the weight, the Hamming weight of E. And if you look at the Fourier transform of this, it can be checked that you get exactly something which is related to the initial probability distribution, but which is a P orthogonal, which has some other here, other expression, which is this one. So in some sense, you transform this Bernoulli distribution into another Bernoulli distribution. So basically, if this Bernoulli distribution actually has small weights, let's say you output typically guys of weight P times N, this one is going to output guys of weight P orthogonal here times N. So you get exactly what I said. If you're able to solve the quantum decoding problem, you're going to output guys of weight P orthogonal times N in the dual, which is probably good. If you do this classically here, you can just show that the decoding problem here if I want to decode errors of weight Pn here, I can find actually in the dual vectors of this weight. But this is not an efficient way of doing this because the classical decoding problem, as I said, is typically there is no good way actually of solving it right now. It would be a terrific result. This something will be changed in the near future. But now, can you do it? Can you do better quantumly by solving a quantum decoding problem? Well, the quantum decoding problem, there will be a regime actually of parameters for which you can solve it in polynomial time. And it is easy to see actually why this works. Because what do you have right now? I tell you, if you let's say the code word is something like this, it's easy to see that you have at the other side, this quantum superposition actually is a tensor product either of psi 0 when you have a 0 here, or a psi 1 here where you have a 1 here. So you have this tensor product of psi 0 and psi 1. These two states are not orthogonal, but what you can do, you can use actually state discrimination to find if it's psi 0, psi 1. If you do this, well, there is sometimes you have an inclusive answer, but you can use optimal state discrimination and using the fact that basically the probability of discriminating the state is actually this probability here, which is related actually to the P orthogonal what we saw before, which is here. You get by doing this, looking at the whole state, performing this unambiguous state discrimination to each position, you get about 2 p perpendicular here times n bits of c here. And if this number of bits is more than the dimension of the code, of course, you can solve and you get the whole code one. And you can solve the problem. Easy. Just solving a linear system. So this problem basically can be solved quantum in polynomial time as long as this condition is met. Great. So what do we have here at the end of the day? If you look at the classical decoding problem, it's either always hard, so we don't have any exponential algorithm for doing this, or in triangular induced regime, but basically there are no solutions. Here now, if you look at what's going on, there is a whole regime of parameters where the problem is actually easy, can be solved in polynomial time. Here, right now, we don't know it's at least there is an exponential time algorithm for doing this just by actually measuring the state and solving it classically, because you can have exponential time algorithm for solving a classical decoding problem. And there is this regime here where we actually, right now, what I said here, we don't know, but now I'm going to explain that you can go beyond actually this. You can actually solve this quantum decoding problem way beyond this information theoretic limit that you have here. So how do you do this? I don't know how to perform the optimal measurement, telling me from this psi of c, the c, but what I could do is perform a pretty good measurement. If I believe that there will be a threshold behavior, meaning actually that the probability that it succeeds drops from almost 1 to almost 0, the pretty good measurement actually is going to give me exactly the point of cutoff here. Just because there is this relationship between the optimal measurement here, distinguishing the states with the pretty good measurement. Okay, there are some technical difficulties here, but we can really understand what's going on for a random linear code for a pretty good measurement here. And it turns out that there is, okay, a whole regime of parameters, which is here, which goes beyond what you can do classically. Which here you can just not solve the problem. You can go this actually problem, you can go beyond quantumly here and go up to this regime. It's still hard here, we don't know how to do efficiently this pretty good measurement in this case, but still actually this problem is solvable beyond this. Basically actually with quantum state that you have more information somehow to solve a problem. Can they view it this way? And now you can say, does it imply something? Well, yes and no. So if you want to use now rigorous reduction in what I say, you have to be a little bit careful because, as I said, there are some technical difficulties in showing that rigorous reduction really works. Because there is some error in doing, the decoding, blah, blah, blah. You have really to be very careful about what you do. But okay, there is a way to do this and prove actually that with this unambiguous state discrimination procedure, you can use rigorous result and get basically something in the dual, as I said. And with pretty good measurement, you have also to be careful because in this case, actually, in the regime when the pretty good measurement works and beyond the unambiguous state discrimination here, you get almost always 0 if you measure it directly. So you have to be a little bit careful what you are doing, but okay, some technical difficulties, but you can be solved. And basically, the picture that we get here is the following one. We can, as I said, we can solve with unambiguous state discrimination here in polynomial time the quantum decoding problem here. This is with a pretty good measurement here. And beyond this, we are sure we cannot solve a problem. Now, if you do this, use this way of solving the quantum decoding problem in regular reduction, you get code words in the dual code. And what are the weights that you get? You get weights actually in this regime here by by using this ambiguous state discrimination here. These guys actually are obtained by using this PGM here. And the unfortunate thing here, if you look at this picture, it's precisely the picture I gave you before for the best classical algorithm. This regime, actually, the classical algorithm, there's also a classical algorithm for doing exactly the same thing. But now we can go into a regime here where actually, even actually by using this reduction here and the best decoding algorithm, you cannot reach, you cannot go up to here. And why is this point important? Because this point is the point where the minimum weight, the minimum distance of the code. So it's actually the minimum weight that you can expect actually to have. Beyond this, there are just no code words available anymore. So really here, this thing, actually what we get here, we have potentially an algorithm for finding minimum weight code, outputting minimum code words in a linear code, which is a very hard problem. Right now, it's still exponential, but it's not clear what we have. So basically, what this thing does, I think really it gives a much more satisfactory quantum reduction in Gregor's basically approach. Because now with this approach, we can really find actually, we can expect to find minimum weight code words in a linear code, which is not something we could do before, first of all. Now, even if we don't have right now a quantum algorithm for solving this hard problem, which is a polynomial time, this approach might give actually quantum algorithms which have a better complexity that we just have right now. So this is a completely new approach. It can be actually interesting to look at. So what I explained right now for the Hamming distribution actually generalized to all product distribution. Is just not what Bernoulli you can do, and basically you can find things about you can use discrete Gaussian distribution. You can put this in it and also find something which is related to the things that I mentioned here. And this is just a paper which is in write-up with André Chailloux and Agathe Blanc, which is here. That's it. Sorry.
Yeah. Thank you for that talk. Questions?
Hi. Do you have any intuition or explanation for why you recover the classical algorithm?
Yeah, well, no good explanation right now, because at some point, we really obtained this with just this inner product of these two states, actually in the square root. Well, there is a way, if you look at what's going on for unambiguous, optimal unambiguous state discrimination, somehow this P orthogonal appears in a natural way, actually. So the only thing that explanation that I have right now, it's the P orthogonal actually appears in the same way as it appears actually in the classical way, but it's not a good explanation. It was not clear at the beginning what it would give the same thing, really. So I still don't have, a very good answer why actually I could transform the classical algorithm into a quantum algorithm and do the same thing. Something looks the same because I also use, in both cases, I use a linear system somehow for doing this. So there is definitely a relationship. But a very good explanation, I don't have it right now.
Do you think it's fundamental?
I would better have a good explanation, yes. I don't know if it's fundamental, but I would prefer having a good explanation.
And then do you mind if I ask another? This shortest integer solution, do you believe this is an exponential speed up? Like you said, there's a regime where there's a...
I haven't tried a lot actually on what they do. It's maybe, and basically they're using the ROG algorithm. The first, if you're looking ROG algorithm at degree 1 is basically what we do, and they use it at a higher degree. And they really tweak actually the R distribution so that it fits the algorithm. If I had to bet, probably.
An exponential speed up
probably.
So like different from Shor's algorithm.
I really think that the quantum decoding problem is easier and that you could do something that you can never do classically. Look, what we are really using here, somehow, when you do this unambiguous state discrimination, what we do in some sense, we perform a unitary and then we measure. And you rotate somehow the error distribution. And this is something that you cannot do classically.
So how did they solve the quantum decoding problem in the paper where they solved the shortest integer?
They use also they also use some kind of unambiguous state discrimination, but it's not optimal. First of all, you can gain a little bit what they do just by using something optimal. First of all, there's definitely something easy to do just using something optimal, and then they get as many bits as possible. They are in a regime actually where the rate is not constant, so they can allow actually to get a better algorithm for solving it, and this is our ROG algorithm.
So it's similar to the thing that.
Similar. It's similar. Somehow it's similar. It's not the same error probability, and they do it slightly different, but some of things are the same. What is new here is the PGM, and what really the PGM, what you can do at the best algorithm for doing it, you can go much beyond actually what we do with unambiguous. So there is something probably to gain. I don't know how much, but there might be something to gain. Yeah.
Thanks. That's very interesting. So my understanding is that there's this result you're probably familiar with from Yamakawa and Zandri that's about getting this sort of exponential speed up relative to random oracles. But in that work,
it's related to this. Actually, it's related to Regev rejection somehow.
Yeah. Decoding sort of arises in a very similar way.
Exactly.
And so I was wondering if you thought about applying the USD type approach to the kind of uncomputation step that arises there, and whether that would sort of give any advantages over what they do in their work.
No, I haven't. It's a good. I haven't good suggestion. Funny suggestion. I knew the paper and I haven't talked about this. Good suggestion.
Any other questions? Okay, let's thank the speaker again.